Good, right? So mechanistically, what's going to happen is we're in strong acid and methanol. So we're going to first protonate the alcohol and hydroxy group of the alcohol. That is going to give a water-leaving group. Right, and one thing that we're going to talk about today is that under most substitution and elimination conditions, OH is a bad leaving group. Just OH on its own, OH minus is a really bad leaving group. Right? So if we want to get oxygens to leave, we usually have to make them leave as water or the alcohol if we're starting with ether. Right? And so by protonating it, we form a really great water-leaving group. Okay? It's going to leave, form a carbocation. And then methanol and add in. So it's serving in this case as both the solvent and the nucleophile. And then the last step, methanol will also act as a base, deprotonate that last intermediate, and that's going to lead us to 2 stereoisomers. One that's going to result from that methoxy coming in from the backside and interacting with the empty p orbital, and one where the methoxy is coming in from the front side and acting with the empty p, interacting with the empty p orbital. Right, so we form 2 distereomers from this reaction. Questions on this? Question on the mechanism, getting the product. Everybody's comfortable with that? Yeah. Okay. So the next question I ask you on the board is: Will these isomers form in a 1-to-1 ratio? The racemic mixture. How many people think they will form in a 1-to-1 ratio? Right. Does anybody not think they're going to form in a 1-to-1 ratio? Maybe. Okay. Right. Do you have reasoning, or you're just playing devil's advocate? That's okay. So let me have you guys think about something. Right. And we're going to think about the structure of this intermediate here. We're going to try to draw this in 3 dimensions. Right, so here is our the orbital that we need to interact with, right? So that's the methyl group and the carbon that we lost the leaving group from, right? And then out here, right, we have an isopropyl group that's going to exist above the plane and hydrogen that's going to exist below the plane. Right? When you look at the structure, do you think there's an equal chance that the nucleophile will add to the top face and to the bottom face? Matthew?
I'm wrong.
You're wrong. Sorry.
There's going to be interactions with the not substitution, it's just
Isopropyl.
isopropyl group.
Yeah. Yeah. So if we have an existing stereocenter on a molecule, right, and we have a face on that molecule that a nucleophile can add either side to, right? If that stereocenter is close enough, right, or the group is close enough to that empty orbital, that group is going to bias the addition, right? So in this case, I can say because this isopropyl group is pretty big, it exists above that plane of the 5-membered ring, when the nucleophile adds, it's probably going to be easier for that nucleophile to add from the bottom face, right? And harder for that nucleophile to add from the top face. Okay, I don't know what the ratio would be, but it's unlikely to be an exact 1-to-1 ratio, right? Because this is going to influence the addition. That isopropyl group will influence the addition, right? Make it just a little bit faster from the bottom face, a little bit slower from the top face, right? So this could be a 60-40 ratio. It could be a 90-to-10 ratio. I really have no idea, right? But we know it's probably not going to be a 1-to-1 because that stereo center is close enough to the new nucleophilic center that it's going to influence the addition to that center. Questions about that? Make sense? Okay. All right, so if this reaction proceeds under the conditions that we've stated on the board with acid and methanol, that's going to lead to 2 diastereomers, right? Not necessarily in the 1-to-1 ratio, but we're going to see both diastereomers. Can we change this reaction at all, the conditions, the reagents that we're adding? Start with the same starting material, but change the stuff over the arrow to make just 1 diastereomer of the product. I'll even give you the diastereomer that we'll make. What's that going to do? So,
Wouldn't it bond like
yeah, so remember that hydroxy group is a bad leaving group.
like, would you still need the acid with it?
So if you add the acid, you're going to form a water leaving group, and then that's going to leave, and you'll still have the carbocation ion.
Does this involve making this an SN1 reaction?
It is not going to be an SN1 reaction.
Because I thought that was impossible, so that's great.
Right? So don't think about how we got to this product before. Just look at the starting material, look at the product, and think about what the difference is.
I remember last class we did like eliminations, and that kind of when we used LI8AL84, like it didn't look good.
So yeah, that's not going to be involved in this reaction, right? So far, or when we looked at this reaction before, we were focusing on this bond here, right? And replacing the oxygen and whatever comes in with that oxygen, put the new group there. But if you look at this, really the only difference is that here we have an OH group, right? Here we have an OMe group, right? So maybe we're not changing this bond, right? That bond is still going back. Maybe we're changing the connection to oxygen, right? So taking that off and putting that on. So how would that work?
Would you use a base to take the oxygen off?
Good. All right. So I'll suggest we use triethylamine. Right. So somewhat hindered amine base. And then what else do we need to do?
It's just nothing.
Methane CH4, right? You can't really do much with that.
CH3.
There's not really such a thing as just CH3. It's methyl iodide. Oh. Okay, so methyl iodide, really, really good alkylating agent. It's actually used in agriculture, unfortunately, to sterilize soils, because it alkylates anything that's organic in there, and it pretty much kills it. So there's actually a few years ago, there was a pretty bad spill of methyl iodide in California in some strawberry fields. Fortunately, it's pretty volatile, it escapes into the air, and so it doesn't stay around very long, but not very good for the environment, but a really great alkylating reagent. All right, so if we look mechanistically at what's going on, in this case, the alcohol is going to be able to add to this methyl iodide, right? So this is methyl electrophile, can easily undergo SN2 chemistry. Create this intermediate, and then the triethylamine will be the base that plucks off that proton and gives us our bond. All right, and this is a name reaction called the Williamson ether synthesis. And Williamson ether synthesis is synthesis of ethers from alcohols under basic conditions. So a substitution reaction, right? But an alkylation of alcohols under basic conditions. Right, so whenever you're making ethers, realize that if you're doing it through substitution, and you're trying to figure out a strategy to make that ether, realize that there are two alkyl groups on either side of that oxygen, right? And so you could potentially start from two different directions, or from using two different alkyls. Questions about this? So let's shift gears here, talk about elimination versus substitution on a practical level. So if you look at the simple schemes up top, you can see when something undergoes substitution, the atom that the nucleophile has to interact with, right? If something undergoes elimination, the atom at the base of the nucleophile has to interact with the proton, right? So for substitution, right, X is going to be the leaving group. The nucleophile would have to come into this carbon, right, whether it's SN1 or SN2, kick out the leaving group. Right? And for elimination to take place, we're interacting with a proton that's 3 bonds away from the actual leaving group. Right? So if you count the bonds between the leaving group and the proton that has to be pulled, right? You have your leaving group, there's a bond connected to carbon, another carbon-carbon bond, and then the third bond is connected to the proton. Right? Very, very easy or very, very common mistake is to, when you're planning an elimination or looking at an elimination, is to pull the wrong proton, right? A proton that's 2 bonds away, or a proton that's 4 bonds away. But for elimination to take place, in this case, right, that proton always has to be 3 bonds away. Right? So just make sure you're comfortable with that relationship. Just like for SN2 chemistry, or for substitution chemistry, there are 2 different mechanistic pathways for elimination. Unimolecular and bimolecular. So in unimolecular elimination, just like in unimolecular substitution, first step is going to be loss of the leaving group. And then the second step is going to be formation of the alkene, or formation of the pi bond. Okay, and just like in unimolecular substitution, the first step of unimolecular elimination is going to be the rate limiting step of that reaction. Right, that's the slow step, forming the carbocation. Right. Bimolecular elimination, the base and the acid, the base and the electrophile, right, are going to be involved at the same time. Right, so the base is plucking off the proton, forming the pi bond, right, all at the same time that the leaving group is leaving. And we're going to get to the same product. Right, and so just like in substitution, we call the unimolecular reaction unimolecular because that's the only, there's only one component of that reaction involved in the rate limiting step. Right, so no matter what the base is, as long as it's going through a unimolecular reaction, no matter what the base is, right, the rate of the reaction is determined by how quickly we can lose the leaving group. Right, concentration of the base is not going to influence the rate because the base is not involved in that rate limiting step. Okay, with bimolecular, there's only one step, right? So that has to be the rate limiting step. you can see in that one step the base and the electrophile interact with each other, right? So if we decrease the amount of base, right, decrease the concentration of base, we decrease the likelihood that those are going to meet up in a reaction flask, and we're going to decrease the rate of the reaction, right? Same thing if we decrease or increase the acid, right, we decrease or increase the rate. Yeah. So if we think about the electrophile, right, the trends that determine unimolecular versus bimolecular reactions for substitution, right, are going to also determine unimolecular, bimolecular elimination somewhat, right? So we can say that E1 or unimolecular elimination can only happen on substrates that can form stable carbocations, right? Because we need to form a carbocation in the rate limiting step. If we can't do that, right, or it's a really high energy carbocation, then that's not going to be a preferred pathway. Right? The difference comes in bimolecular elimination, right? In bimolecular elimination, I don't want to say that the electrophile structure doesn't matter, but bimolecular elimination can happen on primary, secondary, tertiary electrophiles. Okay? So just keep that in mind. It's, you know, we're often not looking at the electrophile to determine which pathway of elimination. So what are the things that influence elimination the most? Right? One is the strength of the base of the nucleophile. Right? Obviously, if we're doing elimination, we want the reagent that we're adding to act as a base, right, and not be able to act as a nucleophile. So let me give you an example of this. Right? So here are two reactions. You can see we're starting with the same starting material. Right? And the only difference is in the top reaction we're using methanol. Right? In the bottom reaction we're using a combination of deprotonated methanol or sodium methoxide, right, in methanol solution. Okay, so in the top reaction we have a relatively weak base, relatively weak nucleophile. In the bottom reaction, because we're using the basic form of methanol, right, this is a much stronger base. So this is going to proceed through an E2 or bimolecular elimination mechanism. Right, before that leaving group can leave, right, before we can form a carbocation, the base is going to be able to pluck a proton leading to the E2 elimination product. of this is that the stronger bases are going to promote elimination over substitution. Right? And so when we're thinking about stronger bases, the stronger bases that we typically look at are things that might be good nucleophiles, right, but are also basic, right? So those second row elements that are, we consider hard nucleophiles, right, or have a pretty small outer shell, right? So these oxygen or oxide nucleophiles, hydroxide, alkoxide, right? There are some amines, regular amines, but we can also have deprotonated amines that are strong bases that promote elimination as well. Any questions about that? Another factor is going to be the size of the base with the nucleophile. So here's another couple of reactions. So you can see in both reactions we're using the same electrophile, right? We're starting with one bromobutane. Top reaction, we're using a combination of sodium methoxide and methanol. Okay. Bottom reaction, we're using a combination of tert-butoxide and tert-butanol, right? So different alkoxide base, right? And then the matching alcohol solvent. Right. First thing, well, we'll look at this first actually. Okay, so you can see the top reaction under these conditions. This is going to proceed through SN2 substitution. Right. Looking at that reaction, how would we know that? How would we know that that should go through a substitution or bimolecular substitution? Right. We're using a polyprotic solvent. So some people might look at that and say, oh, polyprotic, this must be SN1. But how would we know right off the bat, just looking at this, that it can't be SN1?
The structure of the electrophile.
Excellent, right? So the most important thing for substitution is going to be the structure of the electrophile. Right? Primary electrophiles cannot undergo unimolecular substitution, right? No matter what the solvent is, you just are not going to be able to form a primary carbocation ion. Okay, so we can use, in these cases, right, we can use polyprotic solvents and be sure that that's not going to really influence the reaction. Okay? In the bottom, we're using a much bigger, much bulkier base, right? And as a result, this is going to be a really, really poor nucleophile. And it's going to be easier for that bulky base to instead, rather than interacting with the antibonding orbital of carbon-bromine bond, right, to just kind of pluck off a proton here, right, interacting with the orbital on the outside of the molecule. Okay, so bulky bases promote elimination. Potassium terbutoxide is kind of a standard bulky base. Another bulky base that's often used is a base called DBU. Right? And DBU is this bicyclic system with a really basic amino group. Right? You'll often see this used in elimination reactions. Right, so small bases can also act as nucleophiles. Right, bulky bases will promote E2 elimination reactions. Right, again, if we compare this reaction to this reaction, you can see we're using the same reaction conditions. The only difference is here we're using a primary electrophile. Right, up here we're using a tertiary electrophile, so that methoxide can actually interact with the orbital here. Can't interact with the orbital up there. Two sterically good. Questions about this? Third factor is going to be the temperature of the reaction. Or the trend that we see is heat is going to promote elimination over substitution. So for substitution, right, we're going to just draw a simple, or for elimination substitution, or to prove this point, we're going to just draw a simple reaction, right, showing X is the leading group and Y is the nucleophile or the base. right? So for substitution, right, you can see we're starting with two starting materials. And we're making two products. For elimination, right, E1 or E2, doesn't matter, right? We're starting with two reactants, two starting materials. And we are ending with three products. All right, so what reaction do you know that relates overall reaction energy to temperature in some way?
Can you repeat your question?
Is that,
Can you repeat what you said?
what, is there an equation that you know that that relates reaction energy, Gibbs free energy of a reaction to the temperature? What is that?
Oh,
Yeah.
Delta G equals delta H minus T delta S.
Delta G equals delta H minus T delta S. And so if we look at this equation, right, the temperature is going to be closely linked or affecting the entropy of the reaction, right? If we look at the substitution and elimination reactions, is the entropy of those reactions going to be the same?
Mhm.
So which is going to be more entropically favored? Yeah, elimination, right? So here we're starting with two reactants, making two products. Not saying entropy is going to be exactly the same, right? But any entropy change is going to be relatively small, right? Here, because we're making more products than we're starting with starting materials, right? We're going to have positive entropy change. Right? And so because in elimination, that change in entropy is going to be positive, right? The temperature of that reaction is going to affect the overall change in reaction energy, right? If the temperature is cold, then that change in entropy isn't going to affect the change in overall energy, right? But as we warm up this reaction, that change in entropy is going to have an increasingly greater effect on the Gibbs free energy, right? So as this T becomes greater and greater and greater, right, the delta G is going to be more and more and more negative, right? So we're affecting the equilibrium of the reaction, right, or the reaction thermodynamics. In substitution, no matter what we do to the temperature, because the delta S is somewhat neutral, right, substitution is just going to be dependent on the change in enthalpy, right? And the temperature of that reaction doesn't affect the change in enthalpy, right, or is not linked to the change in enthalpy, and so is not going to affect the Gibbs free energy. So by heating up these reactions, we can often promote elimination over substitution. Questions about this? Okay, we'll end there. When we come back on Friday, we'll get into looking at different regioisomers of elimination, and we'll also look at the orbitals involved in elimination.
You said as temperature goes down, delta S goes up and then delta G goes down.
to primary. So it's good. So if you put this together and you heated this up, right, you probably form something. Makes sense? It's an easy puzzle today.